You ever have that feeling where you know you learned something important back in school, but the details are just a little fuzzy now? Well, today we're going to crack open a ninth grade chemistry worksheet and see what we can remember about the basic rules that run, well, everything.
And here it is. I know, at first glance, it might look a little intense, but trust me, all the logic is right there. We're going to break this whole thing down, piece by piece, and kind of crack the code together. You ready? Let's do this. So, here's our roadmap. We're going to start with the absolute basics, the atomic blueprint. Then we'll see how those elements start coming together. After that, we'll get into the rules of reaction, take a special look at gases under pressure, and finally, we'll connect all of it to the world around us. Okay, first stop, the atomic blueprint. Look, to get any of this, you have to start at the beginning, right? And the beginning is the smallest, most fundamental piece of the whole puzzle, the atom itself. It's such a simple definition, but the idea is just huge. I mean, think about it. Literally every single thing you see, touch, or even breathe is made up of these incredibly tiny units called atoms. They are, for real, the Lego bricks of our entire universe. But even these little Lego bricks have smaller parts inside. You've got your protons, which have a positive charge, then you have electrons with a negative charge, and finally you have neutrons, which, yeah, just like the name sounds, are totally neutral. No charge at all. All right, let's do a quick pop quiz, pulled straight from the worksheet. Based on what we just talked about, which one of those particles inside the atom is electrically neutral? Yep, you got it. It's the neutron. And it's this fundamental balance of positive, negative, and neutral charges that gives every single element its own unique personality and properties. So we've got our atoms, but they don't just hang out by themselves, right? They connect, they link up, they bond. So let's dive into the art of the chemical bond. Now, there are two main ways atoms get together. In an ionic bond, one atom literally transfers an electron to another. You can think of it like it's giving a gift. But in a covalent bond, the atoms share electrons instead. It's more like a friendly handshake. This whole transfer versus share thing, it's a huge concept in this worksheet. And here's the perfect example to make it stick. In table salt, the sodium gives an electron to chlorine. That's an ionic bond. But in a hydrogen gas molecule, two hydrogen atoms get together and share their electrons. That's a covalent bond. The whole game is just about whether those electrons are given away or shared between them. Okay, so we know how atoms bond. Now we get to the really fun stuff, chemical reactions. This is where things really start to happen, where stuff changes, combines, and transforms into something new. But first, we got to be clear on the two types of change. A physical change, like ice melting into water, just alters the form. It's still H2O, right? But a chemical change, like a piece of iron rusting, actually creates a brand new substance with totally different properties. That's the real key. All right, this one is a big deal, and it's pulled right from our source. You've got an assertion, and you've got a reason. So, is the assertion true? Is the reason true? And most importantly, does the reason actually explain the assertion? Just take a second to think about it. And the answer is a big yes to all of it. This is a core principle of all of science. The entire reason we have to balance equations is because of the law of conservation of mass. You can't just have atoms disappearing or popping up out of nowhere during a reaction. Everything has to be accounted for. It's a fundamental rule of the universe. So how do we actually do it? Well, let's take this example. If you look on the left, you see one hydrogen and one chlorine atom. But on the right, you've got two of each. So to fix that, we just put a big 2 in front of the HCl on the left. Boom. Now everything's equal. See? It's not some kind of magic. It's just careful accounting. Okay, let's switch gears for a second and talk about one specific state of matter, gases. It turns out they follow some really interesting and, believe it or not, predictable rules, especially when you start playing with pressure. This is Boyle's law, and the idea is actually super simple. Just picture squeezing a balloon. As you increase the pressure with your hands, what happens? The balloon's volume gets smaller, right? It's the same reason scuba divers have to be so careful when they come up to the surface. The water pressure around them decreases, which causes the air in their lungs to expand. It's a perfect inverse relationship. So far, we've been talking about tiny little atoms, bonds, and reactions, but now I want us to zoom all the way out and see how these tiny molecular rules can have a massive, and I mean massive, impact on our entire planet. Here we go, another assertion and reason, and this one is probably pretty familiar. So, again, is the connection correct? Does the reason actually explain the assertion from a chemical standpoint? And yes, absolutely. This isn't a political thing, it's a chemical thing. The actual molecular structure of gases like carbon dioxide lets them absorb heat that would normally escape back out into space. The chemistry of the unbelievably small has a direct impact on the climate of the very, very large. Okay, let's tackle one more big environmental issue that's brought up in this worksheet. You see a few gases listed there, but which one is the main culprit when we talk about acid rain? And the answer is sulfur dioxide. When SO2 gets pumped into the atmosphere, it reacts with water and oxygen up there to form sulfuric acid. And this is the exact same chemical reaction that the worksheet is hinting at when it mentions acid rain damaging marble statues, because acids are really, really good at eating away at that kind of stone. And that kind of brings us full circle. We've gone all the way from a single tiny atom to the climate of our whole world. It turns out the rules are exactly the same, it's just the scale that changes. So it leaves us with one last big thought. If we understand the chemistry of the reactions that cause harm, what new reactions can we design to build a better future?